Okay, welcome everybody to this HEP-TN Seminar. Today we are very happy to have to welcome Ashley Milsted, and she will talk about collision of force vacuum bubble wars in quantum spin chains. So please take it away.
Okay, well, thank you very much for inviting me to give one of these tensor networks in high energy physics seminars. I see you have a lot of nice speakers on your list already, so hope I can live up to that. This is work with grad student at Caltech, Junyu Liu, John Preskill, and Gifrey Vidal, who's now working for some Alphabet subsidiary related to Google also. Now, without further ado, I'll get on to talking about these collisions of false vacuum bubble walls. So first, what is a false vacuum? Just in case you're not sure what that means. The concept is a little bit, let's say, loose anyway. But the basic idea is that if you imagine you have a quantum field theory, let's say, there's usually an effective potential you can write down in terms of the quantum field, in this case, some scalar field phi. And there are situations in which there are two or multiple minima of that effective potential. Now, if there are multiple minima with the same minimum, then that's the situation of spontaneous symmetry breaking. But if you add, for example, some field that breaks the symmetry that is otherwise spontaneously broken, then you can shift some of these minima above the others, and you end up in a situation where, although locally this now higher minima looks a bit like a vacuum, it's actually a false vacuum. It's got a higher energy density than the true vacuum, which is down here on the other side. So this is an explicitly broken symmetry. So you can achieve this in maybe your favorite model by starting with spontaneous symmetry breaking and then adding a very weak perturbation that breaks the symmetry explicitly. And there are processes that can take you from one place to another. So if you were in a false vacuum state for some reason, then, for example, the tunneling process might take you to the true vacuum. And what might that look like? Well, if you imagine, for example, that the universe that you observe every day is in a false vacuum state, then the tunneling process might look like you making an observation at some particular location in space and time of a small bubble of true vacuum. There's always a small chance of that happening. And if you do observe a small bubble of true vacuum, then that true vacuum in your branch of the wave function will be realized and will start to expand because it has a lower energy density inside than outside. And it will start to expand. The walls of this bubble will accelerate and they will approach the speed of light, and they'll engulf the entire universe ultimately. So you probably don't want such a tunneling process to happen in front of you in real life. Some people think that we really do live in, or we might really live in some such metastable false vacuum state that could decay at any moment to the true vacuum. But of course, you have to make a lot of assumptions to come to such conclusions. But nevertheless, so the situation we'll be considering is where you have already seen such tunneling events. So maybe you started with the false vacuum, but then in two different locations or more than one different location, some bubble of true vacuum formed, and those bubbles have walls, and the walls accelerate outwards, and eventually two walls will collide somewhere. And we're considering this situation in one spatial dimension. So in the middle, this is the remaining false vacuum. And on the outside, on the left and right, you have true vacuum. And in between, you have the walls rushing toward each other. And there'll be some collision of these walls. And when these walls collide, well, some particles will generically be produced. And what we're interested in is what happens during these collisions. So can we simulate the dynamics of such bubble wall collisions? So of course, you'd love to be able to do this in the standard model of particle physics, but of course that's just a very complicated interacting QFT. It's way too hard to do. So you might consider a baby version of the problem in field theory. Quantum phi to the 4 theory, for example, in 1+1 dimensions is already way simpler. You can do perturbative calculations in this theory at weak coupling, but not at strong coupling. And so we'd like to be able to consider collisions where strong coupling effects are important. So you might consider putting that theory on a lattice and considering lattice phi-4 theory or similar. Then you can do some numerical simulation, simulate the real-time dynamics using, for example, tensor network methods. But of course, you still have to truncate the bosonic Hilbert space of each of these bosons that you have at the lattice sites. So we take the even easier option of trying to simulate something analogous in a spin chain. So this could be a chain of qubits, for example, the Ising model. You can do the tensor network simulations, and we don't need to do any truncation. And we can set up the basic situation that I described, where we have false vacuum and false vacuum bubbles and bubble wall collisions. So we like a spin chain, but a spin chain where the simulation of the bubble wall collisions is actually interesting, which is a point I'll get onto later. The other thing about a spin chain, so just to make a connection back to the continuum, it seems like we might have lost that along the way. Of course, we can tune to some critical point, and critical points are often described by emergent relativistic field theories, such as conformal field theories, and in nearby a critical point at some relevant perturbation of some conformal field theory, and typically some relativistic massive quantum field theory. So by tuning close to a critical point, we can access the dynamics at low energies, at least, of some quantum field theory. Okay. And the other thing about spin chains, of course, is that you might hope to be able to do these simulations not only with tensor networks, but if you find the tensor network simulations are too hard and you can't reach long enough times, for example, you could potentially do these simulations on kind of near-term quantum computers. We don't expect quantum computers in the near term to have like thousands and thousands or millions of qubits, but a few hundred might be possible. Okay, so in the spin chain, of course, the situation looks very much like the diagram I showed you before, except now it's discrete. So you have some upspins representing the true vacuum and some downspins representing the false vacuum with fluctuations. And then you have some sort of domain wall-like excitations, topological excitations, representing the bubble walls. And in the false vacuum scenario, where you've split the symmetry, broken the symmetry slightly, and these walls will rush inward to try to eliminate the false vacuum. So the project is to construct good false vacuum bubble states to initialize dynamical simulations. So we want to have our initial state for our time evolution of some bubble of false vacuum with true vacuum on the outside, so that we just consider the walls we're interested in. We want to simulate their collapse in real time, and to do that, we're going to use an infinite matrix product state ansatz. And we want to characterize, as far as possible, the emergent continuum physics near a critical point of the spin chain. So we want to avoid any lattice effects as far as we can. And we'd like to understand the computational requirements of this sort of task. For example, as you increase the collision energy and the number of particles you might produce in the collision. So how far can MPS take you? At some point, we suspect that the entanglement growth might just be too high, and you'll have to let quantum devices take over. So here's a summary of the results. So we can indeed create good bubble wall, false vacuum bubble states consisting of 2 bubble wall wave packets. They're good in the sense that the bubble walls are stable. They maintain their form. They don't decay into other particles until they collide, which is what you would expect from this situation. There's no reason for them to interact until they collide. we observe in the Ising model, the simplest spin chain you might pick, that the collisions, however, are kind of boring. They're elastic, no particles are produced. If we go to the extended Ising model that we then decide to study, then we can produce inelastic collisions, which is good, and then we see particle production. We look at the entanglement and how it scales with energy, and we find that it does indeed increase with energy. So you would expect ultimately to exhaust these methods, but in our simulations, we were still able to do them. And you need reasonably large system sizes in order to set up the problem so that you do indeed have stable bubble walls, stable wave packets representing the bubble walls. And part of that is avoiding the inevitable spread of a wave packet with time. If you make the wave packet big enough, then the spread becomes small and things do not delocalize during your collisions too much. Okay. So I'll say something about the methods, unless there are any questions about anything I've said so far.
Yeah, what do you mean by particle production?
Okay, I mean quasi-particle production, I suppose, if that helps. So, in the spin chain there are quasi-particle excitations. You can think of the bubble walls between the true and the false vacuum as being a sort of topological quasi-particle. And if they collide, they can, in principle, scatter into, for example, non-topological regular quasi-particles that then fly away. So you can think of the initial, another way of thinking about this is the bubble walls are confined particles because of the symmetry breaking. So they always want to be together. They're confined by some string of false vacuum, if you like. But if they collide, they can produce unconfined particles or other confined particles for that matter, and those can then fly away.
So unconfined particles are just little regions where the spin is, for example, up as opposed to down or something like this? Or...
Right, it's analogous to that, yeah, exactly.
Thanks.
And in this vein, I would like to ask, so this confinement, one might call it a meson state in the spin chain language. So, but on the other hand, that seems very different than a vacuum bubble. So how can I relate these two pictures?
Well, so they are in general different, but in some cases I think they, well, okay. So in 1+1 dimensions, they're kind of very similar. A vacuum bubble in higher dimensional space is, of course, some extensive thing with a big volume, and a meson remains like two particles separated by some kind of string. But in 1+1 dimensions, the vacuum bubble also kind of looks like a string. Yeah, it's one-dimensional. So that's one thing. Another thing is that, of course, a meson could have some, various kinds of string. It could have excited strings. The string could break, perhaps, due to some process. Here we're considering strings that are built of false vacuum, which is a way of saying they're extremely stable strings. They're metastable strings, if you like. So even if you pull these two confined particles very far apart, the string will not break, or at least it depends what you mean. If you're considering breaking processes through tunneling, I suppose it's possible, but the tunneling probability is very small. So does that help answer your question? So that they are very similar, and you could think of one as the other in this 1+1 dimensional setting. But if you had a very excited string in your meson, then that wouldn't really be a false vacuum bubble. You might be able to think of it as a false vacuum bubble where there are some excitations in the false vacuum.
Oh, okay, I see. Thanks.
So Ash, hi, long time no see.
Hi, Miguel.
See you. So from the purposes of the algorithm that you're using, like, would it be any different if you were to collide, say, a meson? I mean, would it be much more difficult?
Oh no, you mean to collide two mesons, for example?
Yeah, exactly.
Yeah. No, that's not. It's easier actually. It's easier to do that. because there's the subtlety in the false vacuum is that you have to take care of the fact that there's a different energy density on either side of this topological quasi-particle. That makes things slightly annoying, but yeah, with a meson, then you don't have to do that. So that's very easy to do. There was work, this is kind of based or very much related to work that came out 2019, 2020 from Frank Verstrade's group, where they looked at quasiparticle wave packets, and they collided scalar quasiparticles, or mesons, if you like. So they didn't see inelastic scattering, but they could have if they pushed the energy high enough, I suppose. Okay, so unless there are any more comments or questions here, I'll continue. Okay, so yeah, so we're using matrix product states, and we're building wave packets or quasiparticle wave packet states to construct our false vacuum bubbles. So these are built out of some components. We need first the true and the false vacua, and then we need to understand how to construct the walls in between. So, we can draw these stick figure illustrations where the true vacuum.
Can I ask you something? Would you say that what is called false vacua is in general can be replaced by scarred state, or are these two very different concepts?
By a what state, sorry?
Scar, like many body scar?
Well, I don't know too much about the many body scars. All I understand is that it's some long-lived, non-thermalizing, like local excitation, and I guess a meson state like this is kind of a scar. Is that useful?
No, I thought if you have any final insight, yes, I have the same feeling, but I was wondering.
Okay. Yeah, I mean, I guess I am assuming, without knowing too much about the scar literature, that this is a kind of, you could think of this as a kind of many body scar. And if you have like this false vacuum scenario where you have spontaneously broken symmetry, but then an explicit breaking of that symmetry, you will get these scars and these non-thermalizing states generically. Yes, okay, so here I've drawn some stick figures to illustrate these states, like all spin up for true vacuum, all spin down for false vacuum, and some simple domain wall for the kink. But of course, really we want to handle the case where we have quantum fluctuations, which is generically what happens if you look at the ground state of your quantum spin chain. So how do we capture those fluctuations? Well, we use tensor networks, obviously. Now, I'm not going to bore you too much with a basic introduction to tensor networks, because this is a tensor networks in high energy physics seminar. Of course, we can represent the quantum state for any many-body system as a tensor network, which essentially means taking the wave function path back to the true vacuum, even though that path does in principle exist. So unless you have questions, I won't say too much more about that. Okay, so we've got true and false vacua. Now we need to understand how to construct these topological excitations, or kinks.
Sorry, Ashley, one question. So is the true vacuum just a product of all spins up, or is it more complicated than that?
No, so that's why I try to emphasize that there will be fluctuations on top of that all spins up state. So, for example, if you take the Ising model in the symmetry broken phase, in the limit of zero transverse field, then indeed you have an all spin, say an all spin up state or an all spin down state as the two vacua. But as soon as you turn on the transverse field, then you have fluctuations and you have entanglement, and then that's when you need to have some some bond dimension larger than 1 in your matrix product state to reproduce it accurately.
Okay, thanks.
It is an approximation. So in having some particular bond dimension describing your vacuum, you're throwing away some small parts of the state, but you can make those parts arbitrarily small by increasing the bond dimension.
So one more question, like now regarding false vacuum. So like if you are in the like close to criticality or very close to criticality, like isn't it harder to find a false vacuum for you? Or
well, I don't think it will get harder necessarily. So we didn't see that it became harder, but we didn't go extremely close to the critical point. But one reason to believe it might not be harder is that in order to follow an RG trajectory, like if you wanted to take a continuum limit, which means going toward the critical point, then for example in the Ising model that means tuning the transverse field to 1, of course, but also tuning the symmetry breaking field, the longitudinal field, to 0. So the longitudinal field goes to 0 as you approach the critical point. Now, that's important because the stability of this false vacuum cooling procedure depends on the longitudinal field being reasonably small. But since it gets smaller relative to the transverse field anyway, we might expect this to continue to work.
Thanks.
Okay. But having said that, there are probably ways of, more sophisticated ways one could pin down the false vacuum and avoid accidentally going back to the true vacuum in this procedure. Okay, so let me tell you about one simple way of getting a kind of false vacuum bubble state before I describe what we actually did. So this is what we could have done to get some sort of false vacuum bubble. And that is to take the vacuum state that we found using MPS and then just flip some of the spins. So we could flip the spins in some region between X left and X right here. And that gives us something that looks kind of like a false vacuum, except that, of course, this isn't the cooled false vacuum state I told you about just now. This is just the flipped true vacuum in the middle here. But, assume that doesn't matter too much. There's still the issue that the domain walls here are really just flipped spin domain walls. They're extremely localized. And so you expect them generically to have quite a large energy. Why is that a problem? Well, it means that they will likely immediately decay into all sorts of different quasiparticles as soon as you start your simulation. And what we want to do is set up a stable false vacuum bubble state that doesn't change much in the initial evolution, aside from the walls accelerating towards each other. We want the particle production to happen at the collision, not before. So one thing you could do to improve this ansatz that I'm showing you here is to smear out the walls of this, this string, if you like, by adding some Gaussian functions here, f left and f right, and that helps to reduce the energy. These things are no longer extremely localized; they're less UV, if you like. That reduces the particle production you would see initially, but these walls will still generically decay into some other topological and non-topological quasiparticles when the simulation begins, even if you've smeared them. I'll show you a comparison later on. I don't know if you can hear the garbage truck behind me. If you can, just let me know and I'll wait a little bit until it's gone. Okay, so I'm mentioning this to contrast with what we actually do.
Sorry, can I ask you a question?
Yes.
So it seems to me that one thing you could have done is the following. Suppose that instead of the picture that you have, which is true vacuum, false vacuum, true vacuum, suppose you remove one of the walls. So you only have the interface, right?
Okay, so you have true and false and a wall in between, right?
Exactly. And suppose that you start with something that's even the vertical line that you mentioned first. It's not even smeared.
Yes.
I agree. So isn't it true that if you take that as your initial state and you do time evolution, it's true that that will produce particles because it wants to relax to the true equilibrium interface. But won't those particles just fly away and eventually you'll be left, they will fly away left and right, and you'll be left in the central region with a true interface? Because that cannot decay because there's a conserved quantity, right?
Yes, so you have to, right, yeah, you can't avoid having some topological excitation in the middle, that's right. So yes, I think what you're saying is basically true. It's just something we don't want to have to simulate, because all of these particles that get produced and then fly away will generate entanglement, and that will make the simulation harder for us to do. Yeah, I think you're right. So if you had some actual process that created a bubble of false vacuum or true vacuum for that matter, then you might expect it to create some mixture of excitations that then, as you say, some of them will dissipate and you'll be left with something stable eventually.
Right.
I think that's right. But we don't want to have to simulate that part.
Okay, thanks.
Okay. All right. So yes, we don't want to end up with unstable walls with relatively high energy, because even though they decay, they will create entanglement in the process, and that makes our simulation harder. So instead, what we do is we really try to create, in our initial state, topological quasiparticles of the system, kink quasiparticles, if you like. And we do this by using a matrix product state ansatz. This is a known ansatz for excitations, for quasiparticle excitations using MPS. It's been known about since at least 1997. But basically what you do is you take your vacuum MPS, and in this case, a true and a false vacuum MPS, and you paste them together with some new tensor in the middle. You could call it an excitation tensor if you like. And this tensor just parameterizes some localized excitation. And so what this might look like is you have a state which asymptotes to the true vacuum on the left and the false vacuum on the right, but in the middle, parameterized by this green tensor, you have some stuff going on. And then the question is, how do you find the green tensor such that that stuff represents a quasiparticle of the system? And there are standard methods for doing this. The standard way to find quasiparticles of the system, kink or not, is to build momentum eigenstates from these states I just mentioned. So you just take the superposition over all positions with a momentum p, if you like, and then you try to optimize the parameters in the green tensor so that this momentum eigenstate is as close as you can get it to an eigenstate of the Hamiltonian. Now you can show that this is a reasonable thing to do in case there are quasiparticles in the system that are separated from the continuous part of the spectrum. So this is an energy momentum spectrum, a dispersion relation. If your dispersion relation looks like this, where you have some branch or multiple branches before the threshold for which is twice the mass gap of the system, before the 2-particle threshold, then you can represent those isolated branches quite well using this kind of ansatz. And by quite well, I mean exponentially well in the bond dimensions involved. And this ansatz delivers the tensor and also the energy of these Hamiltonian eigenstates. So it delivers a dispersion relation for the system that tells you something about the excitations involved. And it works, as I say, in the topological excitation setting or the non-topological setting. Now, in our situation, I should say, we have a true and a false vacuum. So there are some subtleties. Sorry, go on.
Can I have a question, please?
Yeah, of course.
So can you, I mean, do you improve the description if you include more green lattice sites in between?
Yes.
What you present seems to be like the minimal thing to do, right?
It's not quite the minimal, because you could just put a tensor on the bond, but yeah, it's basically it's rather minimal. You could improve it by having your green tensor encapsulate multiple lattice sites, or having multiple green tensors in a row. So we didn't find that necessary in this case, but it is something you sometimes need to do especially if your vacuum state doesn't contain very much entanglement to begin with. So for example, if you try to do this with the AKLT model where the ground state has an exact bond dimension of 2, you need to include multiple sites in your excitation tensor. Otherwise, you get a very poor approximation to the quasiparticles in the system. But if you like, this green tensor is pulling on the entanglement strings that are already present in the vacuum to approximate the excitation. And the more entanglement there is, the more likely that is to work without needing too many parameters.
Thanks.
Yeah. So apart from creating momentum eigenstates with these quasi-particle position states, you can also create localized wave packets. And this is something that was looked at very recently by Verstraete, Martin van Dam, Lawrence van der Straten, and Jutta Hagemann, and de Naudis. Yeah. They show that you can create these wave packet states. You just take these position states, have some wave packet function f. Well, actually, this is kind of a simplified version of what they did, but it's essentially the same thing. So you take some wave packet function, it could be a Gaussian. If you make this Gaussian quite narrow in space, then what you have is some excitation, which if you think of it, the Fourier transform of it has some support on the dispersion relation of the quasi-particle that you're interested in. And the narrower it is in space, the more delocalized it is in momentum, and the higher the energy will be. But if you delocalize in space, if you make the wave packet broad, then you can focus it in momentum space and reduce the energy. At least, I'm assuming we're at 0 momentum here, then the energy will be reduced. And we want to look at these broad wave packets because we don't want them to spread too much during the time evolution. So that's something I'll get onto a little bit later. Okay, but if you accept that you can build these wave packet states from these...
Sorry, actually,
yep.
Aren't you anyway dealing with a kind of linear dispersion relation or not?
Right, so close to the critical point, at least near to 0 momentum, like at the bottom of this part of the spectrum, you should see an almost linear dispersion relation.
So it doesn't really matter, right? Because everything will spread at the same speed.
Well, it's not linear at 0 momentum because there's a mass gap still. So we're never at the critical point. So it's always, so if you start at 0 momentum, you do still have to worry about this. But it's true that if you were to start your wave packet at some non-zero momentum in like the linear part of the dispersion relation, then you wouldn't have to worry so much about spread. The trouble with that in the false vacuum setting is that that is equivalent to well, okay, there's an issue with avoiding lattice effects. You don't want your excitations to reach momenta that are too high during the simulation, because then you go past this linear part of the dispersion relation and you start seeing significant lattice effects. But if you're sufficiently close to the critical point, you should be able to do fine. Okay, so if you're convinced that we can use these quasi-particle green tensor thingies to construct topological wave packets representing kinks, then we have the states that we need, and we can continue. So the initial state for our simulations, it consists of 2 of these wave packets. We have 2 green tensors, one for the kink and one for the anti-kink. We have false vacuum in the middle, and we have true vacuum on the outside. And we have 2 wave packet functions for deciding how much to smear these excitations out. So in our simulations, we just choose these to be the kink and the anti-kink quasi-particles of lowest energy, but generically there might be multiple levels of kink-like excitation, but we choose the lowest energy ones. And then we evolve in time, and to do that we use the time-dependent variational principle with some methods for bond dimension expansion. And we do this within a finite window of the infinite chain that we started with. And the window can grow if you need it to, but we don't grow it in our simulations.
And do you have absorbing boundary conditions, sorry?
No, we don't. No.
Okay.
No. Basically, it depends on what we want to study. But if we're interested in the particle production, we initially just make the bubble big enough so that we can characterize the particles before they hit the walls, if there are such particles. We could, if we wanted to, I suppose, try to absorb those particles and continue seeing things boil off at later times. That might be a way of, reducing the entanglement at longer times, actually. So that's kind of an interesting thing to consider.
Sorry, what do you mean with a finite window of the infinite chain?
That just means that you have your infinite MPS, but you only allow some contiguous set of tensors to vary with time, essentially. So you can, if most of your state is the true vacuum, then of course most of these tensors will not want to evolve anyway, until some excitation starts traveling in that direction, right? So you can, so this is a good approximation. You're not really making any error as long as the tensors near the boundary that you've artificially set are essentially the true vacuum. And when that stops being the case, then you either need to expand the window or you need to discard your results. Okay. So it turns out we can also use these quasiparticle states that we use to construct the kink and the antikink to detect particles as the simulation proceeds. So for example, if we take the same set of states that we use to construct the bubble, these Kink-Antikink states, we can just look at the overlap of the state as it evolves with that basis in order to see how much of the wave function is still in the Kink-Antikink sector, if you like. And we can do the same thing with, say, a single meson with true vacuum on both sides, or two mesons with true vacuum in the middle as well. Now, there are some subtleties regarding making sure that in the case of two particles, the two green tensors are sufficiently far apart that you can neglect interaction effects. So you have to set some minimum separation there to make sense of this. If this is sort of equivalent to considering asymptotic states in scattering theory.
Sorry, actually, I would have expected that so 2A would be different. So I would expect that somehow the topologically trivial and the non-topologically trivial excitation can be described by different tensor. Is it?
Oh yeah, sorry, that's just a misleading diagram. So yeah, okay. I'm using A and B in all of these cases, but what I really mean is these tensors are different for each of these excitations, but A parameterizes like the level of the excitation in each sector, if you like. So it could be the 8th meson or the 8th kink, but those tensors will be different. Yeah, that's an important point. Okay. Okay, but in principle, we can use these to detect quasiparticles. I should mention there is generically some momentum dependence of these tensors. So we found these green tensors for the quasiparticles by solving some effective Hamiltonian using the momentum eigenstate ansatz, and there is some dependence on the momentum. So to take care of that, what you really need to do is project not onto the position states, but onto momentum eigenstates with the correct momentum dependence taken care of. So essentially, you can do something like a Fourier transform of these guys and do a better job. Okay, so let me just say briefly what the model is that we looked at. I've been talking about the Ising chain, but we add some extra terms in order to see inelastic scattering. So we look at a modified Ising chain with both Ising and tricritical Ising criticality. So in the spin chain, for our purposes, we just want to have at least one false vacuum, and we'd like to ideally see bubbles collapse and bubble walls collide inelastically. The Ising model by itself wasn't quite enough for the second thing, so we look at this model, which is the transverse field Ising chain with a transverse and longitudinal field, and this lambda term here, three-body term, which was studied by Edward O'Brien and Paul Fendley, and also Sanomiya and Hosho Katsura. And it's nice because if you turn the H field off, you turn G to 1 to criticalizing, and then you tune lambda to some reasonably small value, say 0.428, I believe it is roughly, then you get to a tricriticalizing point. I'll show you a phase diagram in a moment. But the nice thing for our purposes is that you can go to the symmetry breaking phase of the transverse field Ising model and then turn on the lambda coupling and go away from integrability significantly while maintaining a false vacuum and have interesting particle production happen.
Ash, can you explain why? Because the Ising model by itself also has a non-integrable region, right?
Yes.
You have both the transverse and longitudinal field.
That's right.
Why
That's right.
wasn't enough for you?
Yeah. Well, we expected it to kind of be enough initially, but it turns out that if you're only close to integrability, we're considering cases where this H field is quite small because we don't want to. Well, because then you probably get a metastable false vacuum that is stable for long times. So you want to have this H field reasonably small, and in that case, you're kind of close to integrability. And it turns out that's enough to see almost exactly elastic scattering. And we're not the only ones who have observed this. There was some literature in recent years of observations of non-thermalizing mesonic states in the Ising model with transverse and longitudinal fields. And some people have tried to make sense of that. I think there was a paper that even used a numerical method to find the approximate conserved symmetry operators that occur when you only have a small symmetry breaking. So there's some sense in which you almost have integrability, at least for certain parts of the dynamics, and we see that here. So I'll show you that later.
Sorry, one more question related to this. I didn't understand your comment about H. So if you make H large.
Oh. H, yes.
H, yes. So that increases the energy difference between the two vacua, right?
Yes.
So I would have expected that then then the difference, so that will make the false, that will make the true vacuum want to compress the false vacuum even faster.
That's right. Yes.
Right, because
yes.
the pressure is much bigger on the true vacuum than in the false.
Yes,
vacuum.
it increases the rate of acceleration of the walls, for example.
Right.
Yeah.
So why is that a bad thing? Why is that not enough?
Right. So, well, the main practical problem is that if you make H sufficiently large, then we can no longer find a good false vacuum state using our method. Right. And the other issue is that let's see. There is presumably an effect on the tunneling rate. If you were to consider events that could cause tunneling from false vacuum to true vacuum, then that's going to be dependent on this H. And for larger H, it'll be more likely to tunnel. And at some point, presumably, these events become so likely that it's no longer reasonable to talk about a metastable false vacuum. But for our purposes, it's just a practical consideration that the numerical tools that we use, which are fairly straightforward and basic in this case, just won't find the false vacuum eigenstate.
I have a question about this perturbation. It seems that you really are coupling the topological and the non-topological excitation, right? So it's a kind of domain wall spin flip coupling. Is it important, or whatever would have done the job that you are?
Sorry, are you talking about the lambda term here?
Yeah. Yes.
Yeah. Yeah. So I actually don't have a super good intuition for why this particular excitation might be important. I mean, you're probably right in what you say. What we find it does in the parameter regimes we looked at is that you end up getting multiple stable kinks. You get multiple stable mesons that can be produced in collisions in principle. And yeah, so at low energies, it looks very similar to, at very low energies, it looks very similar to the transverse field Ising situation. But there are more accessible low energy branches in the spectrum that can be interesting for us. So, you know, you could, for example, choose to do a collision with higher energy kinks in this case. But yeah, in terms of what this means about, you know, whether you can think of these kinks as bound states of something and something else relative to the Ising model, I don't really know. We didn't really look at small lambda. We didn't really look at it as a perturbation.
Because it creates again, it couples one kink or two kinks actually with a spin flip, right? So it couples.
Yeah, I see what you mean. Yeah, so I guess I don't really know how to think about that, but if you have any if you have any insights as to what that might do, I mean, as I say, we didn't really look at it perturbatively, or at least we kind of did try to turn it on just a little bit, but that didn't help us see inelastic scattering very much. We had to go quite close to the tricritical point to reliably see inelastic scattering, where this lambda is then like of the order 0.4 or something. Okay.
Okay, sorry, so one more question. So
yep.
I see why your H term breaks your Z2 symmetry, but I don't really see why your lambda term does.
Oh, the lambda term doesn't break the Z2
yes,
symmetry.
So then what do you mean then? So you don't have the false vacuum if your H just equals to 0, right?
That's right. That's okay. Right. So H, right. For G, I'll show you a phase diagram. Here's the phase diagram. So for H equal to 0, lambda is on the vertical axis, G is on the horizontal axis. G equal to 1, lambda equal to 0 is critical Ising. There's an Ising critical line as you increase lambda, and eventually it ends in a tricritical Ising point. Now, on the G less than 1 side of this line, at least if you don't go too far, you generically see spontaneous symmetry breaking. And if you then turn on this H field, you generically see a vacuum splitting and a false vacuum situation where you have confined particles, mesons. Does that help?
For lambda infinite, isn't it the cluster state or not?
Oh, is it? It's kind of like, it looks kind of like the cluster state Hamiltonian, right? Well, yeah. I can't remember whether that's exactly this or just similar, but yeah, maybe it is. One other way of looking at these perturbations is in, you know, what is their interpretation in terms of the CFT you're close to. So in terms of the Ising CFT, this lambda term is essentially a TT bar operator to good approximation. So if that means anything to you, great. If it doesn't, don't worry. But essentially, if you know that and you know a lot about CFT, if you're Samologikov, for example, then you would expect to see a tricritical Ising point somewhere along this line. Anyway, that's the phase diagram, and we look at a point on the Ising line down here, and we look at a couple of points getting closer to this tricritical point here. And you know, if we'd had more time and spent like doing a lot more simulations, we could have taken some continuum limiter log an RG trajectory, perhaps toward this tricritical Ising point. I think that might be an interesting thing to try to do at some point. Okay, so let's get on to some results then. So first, I want to convince you that the kinks that we're building with this MPS ansatz are behaving as you would expect them to do, as you know, are behaving as topological quasiparticles, in other words. So if you create a single initial kink, then, you know, if it's a quasiparticle, it shouldn't decay into other particles. It should just, you know, either sit there if there's no symmetry breaking, but in the false vacuum situation, it won't just sit there, it will be accelerated towards the false vacuum. And so this initial kink is indeed accelerated. This is the spin expectation values, by the way, as a function of position. So this green curve is at some early time. And then as time progresses, you can see it's accelerating. So far, so good. If you look at what happens over longer times, and now I'm going to switch to sort of a top-down view where the spin is represented by color. So we've got now a single kink. There's no other kink in this system. It's just a single kink. We've got a true vacuum on the left, and we've got a false vacuum on the right. So you start off this single kink at zero momentum, at time zero, and then it does indeed accelerate in the direction of the false vacuum towards the red. But then strange things start to happen, and it slows down, goes back to zero velocity, and turns back around and goes back to where it started. So that might seem a bit strange, but it's actually precisely what you should expect from such a lattice excitation. And the reason, okay, first of all, let me stress again that this is evidence, first of all, that this kink is a stable excitation. It didn't decay into any other particles, even if it did behave strangely. But these oscillations that we're seeing have a name. They're called Bloch oscillations, and they are related to the dispersion relation on the lattice. So if you had a relativistic dispersion relation, you wouldn't see them. But because the lattice dispersion relation deviates from a relativistic dispersion relation, you have to see them. So the dispersion relation of a kink, if we normalize the initial energy to zero, initially starts to look quite linear and relativistic, but on the lattice, it must inevitably curve back around. On the lattice, there is a maximum momentum, pi, if you like, and the momentum is periodic. So when you go past pi, you go to minus pi, and then eventually you go back to zero. So because it's periodic, this function has to behave in a periodic way. And so what you see is that it becomes sort of linear, but then it curves back around, and at pi, it's the gradient is almost zero again. And if you continue following this, it'll go back around down to zero when you get back to where you started. Now, this is important because the velocity of a wave packet of one of these quasiparticles is dependent on the gradient of this dispersion relation. So if you have a wave packet with momentum p, then the gradient of this dispersion relation at momentum p determines the velocity of the wave packet, the group velocity. So if you compare the prediction from the group velocity from the dispersion relation with what you see in the simulation above, then you find it matches quite nicely. So this is the prediction from dE by dP, the group velocity from the dispersion relation, and this is the velocity as measured from the simulation by just looking at where the kink is in terms of the intercept of the spin expectation values with the x-axis. So that's again evidence that this kink is behaving in dynamical simulations as you would expect it to behave. Now, we don't want to see these Bloch oscillations in our simulations because we don't want to see these lattice effects. We want to get at the emergent dynamics of the QFT. So in our simulations, we will try to set things up so that our kinks never get to a high enough momentum that Bloch oscillations start to happen. So we'll try to keep the momentum before this red circle, below this red circle over here, as far as we can. Okay, so let's look at the dynamics of some bubbles. Here are some simulations near the tricriticalizing point and near-ish the tricriticalizing point at lambda 0.3, g 0.9. And these are two different, these simulations have a very similar initial state where the kink and the antikink are separated by some fixed amount on the left and right. The difference between the left and right is that the longitudinal field strength varies. So H is 0.003 on the left and 0.0069 on the right. And that changes the energy of the initial state, because the larger the value of H is, the more energy is contained in this false vacuum bubble. So relative to the gap, the left simulation has an energy of 1.8 and the right simulation has an energy of 2.74. And that means that on the right, you might expect to see particle production because you have enough energy to produce at least 2 of the lightest particles in the system. The gap is the gap to the lowest energy meson, just to be clear. And indeed, that's what we see. So on the left, we see some bubble which sort of smears out as time evolves, but on the right, we see some ballistic excitations propagating away from the first collision here. So far, so good. It's possible to see inelastic collisions with this near this tricriticalizing point. And
sorry, one question. Why don't you see these ballistic particles going out in the plot where you plot the expectation value of Z? In the top plots.
Oh,
you
do. They're just very hard to see.
Okay.
So that you can very slightly make out something just here. If you look, if you zoom in on the smaller spin values, you can see it more clearly. But it's a lot easier to see in this plot of the log energy density.
But don't these particles going out carry a value of Z that's order 1 different from the true vacuum?
Yes, I think that's right. But you have to.
I would have expected those faint
but there is a
lines.
density in front.
One second, let me finish 1 second. I would have expected those faint lines going out at 45 degrees to look red.
To look red, yes, right. So you might see that if it weren't for the fact that this wave function is sort of diluting that effect, because in the scattering outcome, you're seeing a wave function consisting of essentially 2 branches here. One branch, you continue to have a false vacuum bubble, and in the other branch, you have these 2 mesons flying out. Now, if the probability of having the 2 meson outcome is small, then that's just a small component of the wave function. And whatever the spin expectation value would have been if you just looked at the 2 outgoing mesons, it's severely diluted by the dominant branch of the wave function, which is the false vacuum bubble. Right? Does that help?
I understand that argument, I think, but I think what that tells you is that you should see blue almost everywhere, but wherever the meson is localized, shouldn't you pick up a very important contribution when you compute the I mean, you could say the same about any particle in Minkowski space, right? You have the vacuum, and then you have the wave function of the particle, which is the wave function of a single particle state is pretty much vacuum everywhere except where the particle is.
Well, so maybe I didn't explain quite well enough. So I think I didn't explain that well enough. So the situation is that this is a scattering event, and there's presumably some associated S matrix. Now, there are multiple outcomes of the scattering process in this inelastic case. But you can't have, so I'm trying to explain, I suppose, why you see a false vacuum bubble continuing in the middle of this system. The situation is not that there is enough energy to have a false vacuum bubble and 2 mesons. That's not the case. There's only enough energy to either have 2 mesons or a false vacuum bubble. What happens during the scattering event is you have these 2 possible outcomes, and the wave function after the scattering event is some superposition of 2 mesons and a false vacuum bubble. And so what I mean by dilution, you're right that, of course, the mesons are localized somewhere, and there, if you just look at that meson outcome, you would see some significant deviation of the spin. But in this combined wave function where you have both outcomes, that's that there's a factor of the probability of that outcome, which if the probability is small, that might be, say, 10%. So then that spin expectation value gets diluted, and it's only 10% of what it would have been if you'd only seen the two mesons. You see what I mean?
Yeah, okay.
Okay.
It gets lost in the expectation value in practice between the two possible outcomes, right? I have also a question, if I may, about two previous slides. The previous slide, you showed a dispersion relation for the kink excitation. That dispersion relation is an analytical result, or did you get it numerically?
No, that's a numerical result. That's
okay.
A numerical result. And actually, it should be taken with a small pinch of salt in this case, because again, these excitations, these kink excitations in a false vacuum setting actually have infinite energy with respect to the gap. There are some subtleties when it comes to getting a dispersion relation for them. Nevertheless, the data seems to match up quite well if you take care of these subtleties. It doesn't matter that much for the purposes of our simulation, fortunately, because all we want to do is be able to create our initial state from two momentum zero kinks.
Can I ask something? So I haven't understood, in that point where you see the flying out mesons, isn't it again the block oscillation that you're seeing?
Well, so there can be block oscillations, but in this case, the oscillation of the bubble on the left and the right, this happens in both simulations, right? This is just the confining force. So if you look at the momentum of the kink and the anti-kink in the simulation, they never get high enough to cross the linear part of the dispersion relation and go into the crazy part. Instead, they're just being confined, right? So you certainly wouldn't expect to see the bubble bounce out to further than its initial position. It started at zero momentum at this position, and due to energy conservation, it can't really bounce out to here, right? So
well, unless you would have some pair production, right? So it could break.
Oh, I see. You mean if there was some string breaking like effect, yeah. If you had that, then things would look very different. If that was a possible outcome, we don't have enough energy for that in these simulations. But yeah, in principle, you could see something like that.
No, I actually don't think it's an energy fact because apparently it's something that people wouldn't expect, but I also see in lattice QCD, or in lattice gauge theory, that basically the string doesn't break. So this is one of these scarce states. Even if you have enough energy, it doesn't break for some reason.
Well, so in our case, the string, is stable. It's false vacuum. There's no way it can break unitarily. It's essentially an eigenstate. If you just have an infinite amount of this string, it'll just sit there. Even if so even if you separated the meson components by an infinite distance, you would never see string breaking in this situation, not unitarily. However, that doesn't mean a string breaking makes no sense. You could still see it as a tunneling event, for example. But there's no unitary string breaking process in that particular case.
Well,
okay.
Sorry, actually, but this lambda term is exactly a string breaking term, right?
I don't know. Is it?
Sure. You flip two spins and the string is broken, right?
Oh, well. It's a string breaking term. So it's got a ZZ and it's got an X. The X flip spins, yes. It flip spins maybe dependent on whether there's a domain wall nearby.
Or maybe, so sorry, what was the Hamiltonian? XX plus Z or ZZ plus X?
we have ZZ plus X for Ising, and then we have ZZX and XZZ for lambda term.
Oh, then you would need a double X, right, to create to break the string. So you would need the XX. You have it at second order in perturbation theory, right?
What? Well, I guess it's it's not obvious to me that these terms break strings, but I just maybe that's probably because I just haven't thought about it very much. But it's a ZZ times an X.
No, what I mean is the standard transverse field breaks the string at second order in perturbation.
Oh. Well, right. So that probably tells you something about the behavior of the all down state, say, the classical false vacuum state. But of course, we're finding the quantum false vacuum state, which includes fluctuations already, and so that's stable under the Hamiltonian. It's essentially an eigenstate. I mean, you could say the same thing even without the longitudinal field, right? So there are in the symmetry broken Ising phase, there are two vacua if H is 0, right? And they're both stable. The fact that there's a transverse field in the Ising model doesn't cause either of those to be unstable. In fact, you have to find, but you have to find the correct vacua with perturbations included, right? With fluctuations included, rather. So I guess that's what I'm saying is happening here. So the even though we have explicit symmetry breaking, there's still some eigenstate with negative spin that looks like a vacuum, even though it's got an infinite energy compared to the true vacuum, and it's it's stable under time evolution, under unitary time evolution. Okay. Of course, with the numerics we have, I can't rule out that it's only approximately an eigenstate, but to numerical precision, it's an eigenstate. And I don't know an argument why there couldn't be a false vacuum eigenstate. Okay. Let me briefly compare these kind of numerics with the other approach to creating false vacuum bubbles I mentioned, which is just to hit the vacuum with a string operator. So I talked about that briefly. This is a comparison. The left column, by the way, is plagued by by a sort of numerical breakdown at around time 150. That's why there's some very acausal horizontal line in the pictures. But the left picture is if you just take the vacuum and you hit it with a string, so you just flip the spins without any smearing, and you can see that, as I was suggesting, that these domain walls are very high energy and a lot of particles are produced. You see lots of ballistic spread right from the start. If you smear those walls out, that's dramatically reduced. This is the middle column. You still, however, see some ballistic propagation from the initial bubble walls. And if you use the quasiparticle approach where you tune the initial state really to be just the quasiparticle you're looking for, then of course you can eliminate those two. And you can see this is reflected in the entanglement entropy that's at the bottom here. There's a lot of entropy produced on the left. In the middle, there's a little entropy associated with these particles that emanate from the initial walls. And on the right, the only entropy before the first collision is inside the walls themselves, and it's quite small and it doesn't change with time. So that helps to make these simulations efficient. Now let me compare the tricriticalizing point, or a slightly different tricriticalizing point, and the Ising case. So in the Ising case, I've set the transverse field to 0.8 and the longitudinal field to 0.007. And these are the parameters for the tricritical case. the energy with respect to the gap on the left is actually enough to produce, in principle, 3 mesons, as well as 2. On the right, it's enough to produce 2, and we do indeed see ballistic meson propagation. But on the left, in the Ising simulation, we don't see any mesons flying out from the collisions, even though, as Mikhail pointed out, this is, there's a longitudinal field that breaks the symmetry, and it's not integrable. Although in some sense, maybe only slightly non-integrable. So to check that in the Ising case, there really is no scattering, even if it's just very small, no inelastic scattering rather, we use these quasiparticle overlaps that I discussed to detect the quasiparticle content of the wave function as time evolves. And this is the probability of not being in the Kink-Antikink subspace. So the initial wave function is in the subspace. So we have a very small probability. There are some numerical errors that we inevitably make, but there's a very small probability of not being in the Kink-Antikink subspace initially. The blue curve is the Ising simulation. So as time progresses, there's a collision. The kink and the antikink interact, and our basis no longer captures that well. So we're no longer in the Kink-Antikink separated subspace. But when the collision is finished and the kink and the antikink fly away from each other again, we find that actually we are still in the Kink-Antikink subspace. So there was some scattering event. We don't know quite what's happening during the scattering event, but afterwards we're still in the Kink-Antikink subspace to very high precision. And as the bond dimension increases, we see that we're converging to like almost the original probability that we started with. So that, to us, is strong numerical evidence that there's essentially no inelastic scattering in this Ising case.
So you're so just to make sure, so you're saying that there's no inelastic scattering of kinks in the Ising with both transverse.
Yes, of kinks specifically.
Yeah. So like it's not really a statement about inelastic scattering of mesons, right? Which should be possible.
No.
To return on the
Right. It's right.
Okay.
We're not talking about that. But if you look at the kinks, this seems to be the case. We didn't test to see if this also happens for mesons. The mesons are kind of annoying to deal with because they can be quite extensive. Anyway, this is in stark contrast to what happens in the tricritical Ising model. If you look at the same quantity, then it's small initially because we're initially in this Kink-Antikink space, but then at the first collision it jumps up again, as in the Ising case, but then it stays up because we produce some mesons, and so there's some probability of not being in the Kink-Antikink subspace associated with meson production. Now, in the tricritical case, we can actually try to identify the outcomes in more detail. And here, what we do is we look at a few different possible outcome sectors. The Kink-Antikink outcome is still possible. So there is an elastic channel, if you like, and the probability for these parameters was about 62% of staying in the Kink-Antikink subspace. We can also look at the 2 meson production rate. That seems to be around 19%. So indeed, that corresponds to the ballistic particles we see flying out. And what we've done here is we've essentially projected into these subspaces and looked at the spin expectation values. So here you can really, the gray curve is what you see in the simulations from the spin expectation value. And we can pick out the branch of the wave function corresponding to the 2 mesons, and we can see the 2 meson bumps in this orange projected curve here. And apart from that, we see there's also good evidence that there is production of heavier false vacuum bubbles, in the sense that one of the kink or the anti-kink is a heavier kink or anti-kink with a larger mass. So that's also possible because there are multiple species of kink in this model. And what we see is that there's a roughly 7% chance of being in that sector. There are 2 of these, right? There's a heavier kink on the left or a heavier kink on the right. And these are kind of harder to spot. They don't separate as well because of the heavier kink. it means that there isn't enough energy for them to fly apart very much because they're still confined. But still, we can use these quasiparticle states to detect these outcomes and characterize them. This becomes harder if you have lots of quasiparticles. Like if you had a 4-particle outcome, that would be harder to do, practically speaking, using these methods, harder to detect. But 2 particles is relatively easy to do.
Sorry, Ashley, one question.
Yep.
These plots are the expectation value of Z as a function of position at what times?
Oh, at one particular time. I'll show you where. This is, I believe, at. Oh, actually, do I know exactly where? I think it's roughly here. It's sort of roughly where the remaining false vacuum bubble is at its broadest. It's roughly here.
Okay. So I suppose if you took a later time, it's just that this probability of 62% to remain in the Kink-Antikink sounds really high.
Oh, well, yes.
I guess it just takes time for this to evolve into a very small component along that branch. Right? If you took a later time, wouldn't you find a much smaller probability to remain in that branch?
Well, so the probability will decrease with successive collisions. So there will be more collisions, right? Because whenever you have a confined pair as an outcome, that confined pair will again collide and produce more particles and so on. So there'll be more collisions. And with each collision, there'll be a smaller chance after that collision of remaining in the Kink-Antikink subspace you started in. But if you didn't have another collision, then these would be the asymptotic outcomes. And I mean, it's kind of an artificial thing to consider because they're confined and you do have another collision. But you know, does that help?
Yeah, I guess it just runs against my intuition. So tell me if my intuition is incorrect. So I think of these kinks and anti-kinks as heavy, very heavy excitations. So, or if you want, another way of rephrasing that is that what you have in between them is a false vacuum.
They're not very heavy in this case.
Okay, so because I would have expected them to have a very high probability to annihilate with each other, and then give you everything that is kinematically possible and allowed.
Right. Okay, yes. So in a realistic, like cosmological setting, if you like, where these where the false vacuum bubble walls have, you know, accelerated very close to the speed of light, then, you know, they would have a lot of energy and you'd get showers of all sorts of particles coming out when they collide. But in our cases, you know, the energy of the simulation is only a little over the threshold for 2-particle production. So these kinks are not very heavy in this case.
Yeah.
So that maybe helps explain why there's a high probability of staying in that sector.
Yeah. Okay. Thanks.
So if we wanted to make them heavy, we'd have to and still see the emergent quantum field theory near the critical point. We'd need to go closer to the critical point in order to be able to reach larger velocities while avoiding the block oscillations that we don't want to see. Right? And then we could get to higher relative energies and see more outcomes and higher probabilities of other scattering outcomes.
I'm not sure that even in that case you would get a very different result because this is a 1+1 model, and in this model the kink and a Kink-Antikink is not so different from a meson. And that's a feature of one dimension. Whereas in high dimensions, you know, a bubble is very different from a particle. A particle is an excitation around a given vacuum.
Yes.
So anyway.
Well, I guess all I mean is that you know, if we imagine the quantum field theory that we're trying to access, you can make the initial kink and anti-kink as far apart as you like. in the QFT. If it's a relativistic QFT, then the further apart you make this, the bigger you make the initial bubble, the more energy you have, and the more chance you have of producing lots of particles when they eventually collide, right? In order to get to that on the lattice, we have to tune quite close to the critical point. That's all I mean.
So in your case, if you started with an energy which is below the gap to produce 2 mesons, would you be guaranteed to remain in the Kink-Antikink sector?
Yes, I think so. So this simulation that I showed you, where we only changed the longitudinal field strength, in other words, the energy density of the false vacuum, kind of shows that. So I don't have the particle basis overlaps here, but you can see there's no ballistic production on the left, but there is on the right. And the only difference is that one is below the threshold for pair production and one is above.
But still, in the top plot on the left, it still seems that eventually you're gonna be left with only blue, right?
Well, so there is delocalization. So that's what you're seeing here. You're seeing that the bubble is delocalizing.
Okay.
Okay, I'm going to briefly talk about entanglement. So entanglement, we can also look at. It's, as I was mentioning, it's very important for these MPS simulations because the higher the entanglement, the harder it is to capture the state accurately using a matrix product state with some given bond dimension. So we'll compare again the Ising simulation and the near tricritical Ising simulation from the previous slide. In terms of entanglement entropy, they look actually kind of similar. It doesn't really seem to make that much difference whether you have elastic or inelastic scattering happening. So what you see generically is that when there's a collision, there's some jump in the entanglement entropy, as you might expect. Lots of stuff suddenly happens. And then after the collision, things fly apart. And while they're flying apart, at least in our simulations, they're not really interacting very much. And so the entanglement kind of plateaus until there's another collision. So here's another collision. In the Ising model, you just have the false vacuum bubble and it sort of breathes. And so each time there's a collision, there's a jump in the entanglement entropy. And between the collisions, there's sort of a plateau. And as things delocalize, well, these jumps kind of get smeared out, but still. And you can see that the simulation is getting, yep.
Can we interpret the jump as by the fact that we don't know if they have reflected or transmitted, and then it's just twice the previous? Is it the case, or?
It's not exactly that. Let's see. Is it? Wait. I seem to remember it's. Is it that? Well, maybe it is that. So basically, it's associated with. So in 1+1 dimension, the only like non-trivial elastic scattering that can happen is you get some phase associated with the momenta of the incoming particles. If you had plane wave scattering, just particles with the definite momentum of p and minus p, say, then you would see no entanglement because there is only one possible outcome. However, we have wave packets consisting of a range of momenta, and because of that, you can see entanglement in the elastic scattering event. There's actually a piece in the appendix that John and Junyu worked on where they show analytically that if you have an elastic S matrix with some phase associated with elastic scattering in 1+1 dimensions, then the entanglement produced between the outgoing particles is dependent on the scattering phase angle and also on the wave packet width. And in the limit of large wave packet width in space, the entanglement goes to 0. So I hope that helps. So we would have, if we'd have chosen, in other words, the wave packet width of our simulations differently, the amount of entanglement you'd see in these plots would be also different. The jumps would be of a different height, I guess. So on the right, we have the inelastic scattering case, and we also see a jump associated with the collision. You can see that the simulation on the right was kind of harder to do. The entropy after the first collision was around 3 in terms of, this is base 2 entropy. We needed to have a bond dimension of around 128 to accurately simulate that. It's kind of converged. We were able to simulate for longer in the Ising case. We could basically get 2 collisions simulated accurately with the same bond dimension of 128. But we're not really that interested in our case in simulating lots of successive collisions. Rather, what we want to do is accurately simulate the first collision and characterize the outcomes of that scattering event. So there, maybe the interesting figure of merit is, what is the entanglement during the first collision, which is where it peaks before the plateau, and how is that related to the energy of the scattering event? So that's what we look at here. So this is entanglement maximum cut entropy versus energy for 2 different parameter regimes. The black curve is probably the most interesting one to look at. This is where we're closer to the critical point and can go to higher energies before encountering block oscillations. So block oscillations happen at some point, and this is indicated by how close we are to that is indicated by the light colored curve. This shows the pre-collision velocity of the wave packets. And if you look at the red curve here, we increase the energy, the pre-collision velocity increases, eventually it reaches a maximum value and then it decreases again. This is because block oscillations are occurring. And we shouldn't really maybe trust the results as indicative of a continuum theory after that starts happening. But at the black curve, we don't quite reach the maximum velocity with this range of energies. So it's probably a reasonably good indication of what happens as you take a continuum limit. And there you see the entanglement entropy continues to increase as we increase the collision energy. By the way, this is increasing the energy by just making the initial bubble larger rather than changing any Hamiltonian parameters. This is just making the bubble larger. I don't think we can say very much reliably about the asymptotics of this behavior here, but it confirms the expectation that the entanglement does indeed increase with the collision energy. It's a little interesting because it increases very smoothly, even though we are crossing various thresholds for particle production here. If you look at the x-axis, we're crossing the threshold for 3 meson production here and 4 meson production here, but the entanglement entropy seems to vary smoothly across those. Maybe worth noting. Yeah, otherwise, if we're interested in finding simulations where MPS isn't enough and you'd need a quantum device to take over, which might be one thing you're interested in, these aren't it. But you have reason to believe you might get there if you can increase the energy sufficiently far. Now that's a problem maybe for this model, because in order to increase the energy further, you need to go close to the critical point. And if you go close to the critical point, you need more lattice sites to do the simulation reliably. And we're already in the thousands of lattice sites, well, around 1,000 lattice sites in our window at the moment. So that seems unlikely to be within the reach of NISQ devices anytime soon. But for other models, which maybe have more complicated dynamics, you might hope to achieve a regime where they can win and beat MPS. But it's hard to beat MPS. Anyway, so the summary is that we can use this quasiparticle ansatz to create stable kinks with false vacuum on one side of them. And we can simulate the inelastic collision of such kinks in a modified Ising chain. And we can, to some extent, verify the particle content of the state post-collision using these quasiparticle basis states. As I was mentioning just now, there's sort of a trade-off in beating lattice effects. We need to beat lattice effects. We need to go close to the critical point to make the system size quite large. So there's still a question of whether there's a regime in which MPS are no longer good enough and some NISQ device with, say, a few hundred qubits could beat it. That's not clear for this particular kind of simulation. That, of course, is not to say that there aren't dynamical simulations you might want to do where MPS will not do the job. This case is actually very favorable for MPS because we've tuned the initial state so that there's not very much entanglement being produced. You know, I want MPS to win. So where do we go next? Well, you know, we'd like to increase the energy. We'd like to be able to, you know, properly take continuum limits along an RG trajectory in one of these spin chains. We'd like to look at harder models, maybe with going near to critical points with higher central charges so that there's just more stuff that can happen in the low energy dynamics. Look at higher dimensions. One way to do that would be to look at a compactified second spatial dimension, which you might still be able to treat using MPS. And another interesting thing you could look at is sort of the flip side of this problem of colliding, of a collapse of a small bubble of false vacuum, which is how does a true vacuum bubble nucleate if you start on the false vacuum? So one way that might happen is if you collided two false vacuum quasiparticles. So here's a sneak preview of what that might look like. These are very preliminary simulations, but this is if you start with the false vacuum, you create two scalar excitations, two meson excitations, if you like, and you let them collide. And then one possible outcome is that you get a small bubble of true vacuum forming that then expands. It didn't expand in this particular simulation, but these were so preliminary, I don't actually know why for sure.
Sorry, actually, one question. So if you prepare the system in the false vacuum and you just evolve it and wait long enough, will it not create bubbles by itself?
No.
Why not?
At least not with our definition of the false vacuum. So what our false vacuum is, for numerical purposes, an eigenstate of the Hamiltonian. So it will just sit there.
Okay, but would you agree that in the exact treatment of the system, there's a non-zero probability for it to simply nucleate a bubble?
Well, I think that depends on what your false vacuum is. So I suspect that there is an exact sense in which there exists a false vacuum eigenstate, or an eigenstate in the false vacuum sector that looks like, what do I mean? Yeah, I think saying there exists a false vacuum eigenstate is not unreasonable. And if you have that state, of course, well, it's an eigenstate and nothing will happen.
But that cannot be true, right? Because if you ask what is the probability that that state tunnels into the true vacuum, that probability is non-zero because the barrier is finite, and that tells you the eigenstate.
Well, but tunneling is a non-unitary process.
Why? No. No. Why?
Well, so tunneling.
Tunneling is quantum evolution. It's unitary.
Well,
if you put a particle in one room, there's a non-zero unitary probability that it will, go to the other room across the wall, and that's unitary.
Right. There's a probability, right, and there's a probability of measuring spin up despite being on the false vacuum, right? There's always some non-zero probability of measuring spin up. It's very small. And there's also some non-zero probability of measuring some large bubble of spin up. In other words, a true vacuum bubble, but it's very small. It's extremely small. So that probability is always there, but that tunneling probability, if you like.
I think it's true that tunneling is exponentially, the probability is typically exponentially, well, it's not typically, it's exponentially small in the area of the barrier, but it's unitary. It's just unitary evolution of your system.
Well, I'm not sure what is unitary. So if there's a small probability of being on the other side of the barrier, are you saying that under unitary evolution that small probability eventually becomes a large probability?
Yes, integrated over long. If you wait long enough, it's a probability per unit time. So if you wait long enough, for sure. That's why phase transitions occur via bubble nucleation, because there's a non-zero probability per unit time to nucleate a bubble that's big enough to expand. So if you wait long enough, you will nucleate it, and once it's nucleated, it will expand.
I don't understand how bubble okay, but okay, so here we have a translation invariant state. Whether or not it's an eigenstate maybe is beside the point, but it's translation invariant. There's no seed to nucleate a bubble. So that there's no unitary process that could cause the local formation of a bubble that makes the state non-uniform in space. It has to stay uniform in space.
Isn't the same question as before about the string breaking, or not?
I think it's very much related to that, yes.
Okay. So if you, for example, add by hand XX term to the Hamiltonian, have you tried that and see if it...
I haven't tried that, no.
Because this brings something that would be, again, second order to first order. And so maybe the probability that David is talking about is just larger.
Yeah, so let me address one of the things that you said, which is correct. Well, it's partially correct, I think. So it's true that both the false vacuum and the true vacuum can be defined as translationally invariant states.
Yes.
So you can ask, why would the false vacuum, which is translationally invariant, decay via bubble nucleation?
Yes, yes.
And by doing that, go into a non-translationally invariant state.
Yes.
And the answer is that state has lower energy, even though it breaks translation invariance. Because if you nucleate a bubble that's big enough, that has lower energy.
But that confuses me because the energy can't change under a unitary evolution.
Yeah, I think that's exactly the point, right? I think that's why it is suppressed, because you have an energetic. It's a kind of this what they call Stark localization. So if you have something where a particle can hop freely, and then you tilt it and you give some energy, different energy to things, then the particle localize. And I think it is the same thing. So there is no resonance that allow you to go to the lower energy state. And that's why I think if you add a term in the Hamiltonian that that kind of connect the two states directly, then you should be able to dissipate this extra energy or somehow. So you have two issues. You don't have a direct matrix element in the Hamiltonian, and then you also have this non-energy conservation that also kind of exponentially suppressing the energy difference, as you say in the tunneling. No.
So I'm confused about this case because this is truly a transition between vacua, which happens at 0 temperature. I know the answer if we were looking at some finite temperature and this was a thermal phase transition, then in that case, the answer is that once you go slightly, ever so slightly below the critical temperature, if you start at high temperature, then you're on the branch that has higher free energy. So it will decay to the preferred state there, which has the lowest free energy. And that's fine because free energy is not conserved because you create entropy in the process. So I'm sure that's, well, I need to think, you have a good point. I need to think about the transition between true vacua, yes.
Yeah, and energy conservation. Maybe exactly. And an exponentially small temperature would change the picture.
Yeah, but I think it's okay to think about 0 temperature. I mean, that's why people who, I mean, in the beginning you referred about whether the standard model is in a true vacuum or a false vacuum. If it really is in a false vacuum, people believe that the way it will decay is indeed via the nucleation of bubbles. So yeah, I need to understand a bit better this issue, but I think, I mean, the universe will evolve according to unitary evolution, right?
Yes. So, well, I guess one thing to say there is that, of course, we're not in the vacuum of the standard model, yes. Right?
No, but so, on large scales, yeah, but it's true.
Yeah.
It's true. Yeah.
I mean, I could certainly imagine, we also have observers, right? And so even if there's no unitary, I mean, you say the we have multiple systems, and we have some systems that we like to treat as observers. We call them humans, and if they observe at some point that a bubble of true vacuum has formed, then it has formed, and it will evolve and consume everything. So if somebody's sitting in a lab one day and they make an extremely unlikely observation, then all is lost.
No, I agree, but I mean, all of this is of course going on a tangent, so I'm sorry to hijack the discussion.
Oh, well, I like talking about it. It's okay.
Okay. I still stand by what I said, that I think the false vacuum decay is a unitary process. And I think the reason you can see that that's true is that if you have these two vacua, which are not degenerate, so one has high energy than the other, you can compute the transition probability from one to the other, for example, in some semi-classical approximation, or you don't have to do it into the approximation, but you can. And
okay, but this
transition probability tells you that that is not an eigenstate.
Okay, well, okay, but you're assuming something about the false vacuum state. You're assuming that it's not an eigenstate, but can there not be a false vacuum eigenstate? Is I guess another question you can ask. Or maybe less confusingly, can there be a false vacuum eigenstate? And if there can, then, well, of course, there's never a transition from that state to the true vacuum. If there can't, then sure.
No, there can be a false vacuum that's translation invariant.
Right.
But I don't think
not an eigenstate. Yes, I agree.
If there's a transition probability to the lowest energy state. Right.
But I'm also interested in the question of whether there can be a Hamiltonian eigenstate that is a false vacuum. Right? Is there a reason to believe there can't be?
If I may comment,
I think if it's a true eigenstate, then it means that you're in some superselection sector that you cannot decay to the other one. And one way to achieve that is to make the barrier infinite between the two. But it depends on your Hamiltonian. If your Hamiltonian has a finite energy barrier between the two, if you write down some effective potential to describe this system, if the barrier is finite, there will be a transition. So it will not be an exact eigenstate. But anyway.
Sorry, somebody wanted to say something. Yeah.
No, I was thinking about this also, if I got correctly the subject. I mean, if this false vacuum is an eigenstate, and I don't see any reason why there shouldn't be a higher energy eigenstate than the ground state, it should just remain itself under time evolution. I mean, it's time translation invariant. But the point here is that you're not evolving the false vacuum only. You are putting excitations on it, right? Those break translation invariance, for example, because you are putting in some position your excitations, and also it's no longer an eigenstate. So I guess that may be the reason why one should expect, even starting from the eigenstate false vacuum, once you put excitation, you may expect a decay, right?
Right. I guess that's true. I mean, we were partly considering what would happen if you didn't do that, if you just had a uniform false vacuum state, because that will also tell you, in the limit of, so you got this false vacuum bubble, in the limit of a large bubble size, well, the middle of the bubble looks just like a large false vacuum, and would you see nucleation within that interior? Is perhaps another question you can ask. And if the false vacuum really is an eigenstate, then I guess the answer is no. But if there can't be a false vacuum eigenstate, then I suppose the answer might have to be yes. But yeah, I don't know. I'm not convinced there can't be a false vacuum eigenstate. I don't see why as you say, why you can't have a high energy eigenstate which happens to have a spin expectation value opposite to that of the vacuum. It's not exactly the reflection of that spin expectation value, by the way. It's not just take the minus sign, it's just on the other side of zero.
But I think practically, even if it's not an eigenstate, but it's locally very similar, there is no difference, right? So from the practical point of view. So I guess
I mean, yeah, right.
One ingredient that locally it's very, so since you have a local Hamiltonian, locally this state is very similar to an eigenstate, and you have to go to very high order in perturbation theory, and this gets extremely suppressed, right?
Well, so it's interesting to consider the state where you just flip the true vacuum on that note. So, I did a very basic perturbative analysis of that. And indeed, of course, there are terms in the Hamiltonian that mean that if you just flip the true vacuum with the symmetry breaking in place with non-zero H, then of course that state is not orthogonal to the vacuum state. So if you were to do imaginary time evolution, for example, you would eventually get back to the true vacuum. Now, on the other hand, this state is, that state really does have exactly the opposite spin expectation value to the true vacuum, by the way. And that's the initialization for our cooling process, where we say, well, that state is probably some slightly excited version of the false vacuum, so let's just cool it down and go to some false vacuum eigenstate. And that's what we try to do, and that seems to at least make sense numerically. But of course, I can't rule out that there isn't really an eigenstate there. There's just something extremely close to one.
Yeah, exactly.
Yeah.
But actually, we also did these experiment that you say. So we create a meson, a large meson, so that basically we have the false vacuum in the middle, and let it evolve. And even the scattered particle don't break the false vacuum, so it stays there forever, right? So we have a finite thing, so this scatter event comes and go, and they stay there forever. So it's pretty amazingly stable. So that's something.
Yeah, I mean, when I say it's numerically an eigenstate, this is to double precision, right? Or maybe single precision, but still, that's very small. So so for the amount of time evolution that we're doing, you're not going to see it change. Yeah.
Okay, may I also comment a bit? So like we studied actually a bit related model, but like in like very different limits. So we considered actually like say Ising model, but with large HZ and small HX term. Okay. And then we actually tried this so we tried actually something like this. So we just initialize system in this bare false vacuum. And then we'll look how it like decays. So like bare vacuum, okay, it's not an eigenstate, and then it can evolve, okay, right? So because we have this, so bare, I mean no HX term, and then we can take a look what happens. And yes, so like if we don't have any special like resonance conditions, then indeed like it just never happens. If we satisfy some special resonances, then yes, it can happen, but we have to wait like really long time. So it's like really like exponentially suppressed. So we have to go to really some high order, like perturbation theory order term. Yeah.
Yeah, I'm now wondering what happens if you just take the flipped false vacuum and evolve it for a long time without doing the cooling process. Just that's an interesting thing to do too. At short times, at least, what you see is some light quench dynamics on top of the false vacuum. So you see some oscillations that are uniform in space. But I wonder what happens if you just go to very long times with that situation. My intuition is that because the energy density is not high enough to create a pair of particles at any local position, you'll still never see decay. But I'm a lot less sure about that.
But again, we also checked for very, very light particles and kind of long strings. And again, it's very hard to, I mean, it never breaks basically. Yeah.
Well, yes. Well, thanks for the discussion, and if you want to continue, that's fine. I guess I should just point out though that I did finish my talk, just in case anyone's feeling obligated to stay.
Yeah, thank you so much for your this very engaging talk, and yeah.
Yeah, it was really great. Thank you very much.
Well, thank you. Yeah, thanks for the stimulating discussion.
I really enjoyed it. Thank you.